Mhm. Okay. Hello. This is weird. I'm talking to myself, but okay. Hi everyone. Let's see. So yeah, so the exam is on Thursday, and I was looking at the um, last recitation's video, and I will upload it, but I'm not like 100% convinced that it was accurate for the critical resolve shear stress. The first part where we talked about recovery, recrystallization, and growth, that was pretty good, but I was like thinking about it. I was like, I don't know if this is right. So I I did some reading over the weekend, and I feel a lot more comfortable with the topic now. So I'm gonna just re-record the lecture, or not the lecture, the recitation, and post this as well. Um, the other thing is I wanted to just take some time to talk about the exam to, kind of reassure everyone. Um, so here we have, this is Blackboard. Um, and again, these are the topics that will be on the exam. A lot of the topics we have discussed explicitly, such as, the ductile to brittle transition, the bonding influence on material properties, the force distance curves, stress strain curves, electron configuration, recovery, recrystallization, and growth, Hume-Rothery rules. But the two things that I want to talk about today are critical resolve shear stress, and then we're going to touch again back on planes and directions. And I think just just for myself, to not feel bad about giving you wrong information. And there's this test of the testing system, right? Here. So if you look at this, it's too early to be thinking. Okay, so if you look at this, these are the type of questions that you could expect to see on the exam. There are things like so the first question says the Burgos vector is a screw dislocation is perpendicular to the dislocation. And so the answer to that is false, because for screw dislocations, they're parallel, and for edge dislocations, they're perpendicular. So that's like a true false type thing. Number two, a family of planes is represented by HKL in parentheses, brackets, UVW, curly parentheses, HKL or D. I don't even know what you call those, HKL. It's C, because it's a family, so they're squiggly, and it's a plane, so it's HKL. Okay, number three, repeatable entry of a crystal structure is known as a crystal, a lattice, a unit cell, or Miller indices. So the answer is C, a unit cell. A crystal can be any size, right? It can be very big, they can be very small. And a crystal is composed of unit cells. So the unit cell is the smallest building block that we can repeat to build a crystal. A Miller indice is like part of the notation from the second question, like the HKL, and that's a way we denote planes and directions. And now this idea of a lattice, right? This lattice idea versus a crystal is kind of interesting. So we could take a moment to draw about it. Let me see. Okay. Fix my hair. All right. So first, let's draw you can't even see that. What? That's better. Okay, that's, oh, there you go. Okay, cool. So, for example, let's draw a lot of these. Cool. So here we have a crystal. And the crystal is composed of blue and red atoms, right? And they repeat in some shape. So the whole thing is a crystal because the whole thing is has a repeating pattern to it. Now, when we want to look at the unit cell, we need the smallest amount of information to recreate this pattern. And to do that, we would go like this. So this box here has the one blue atom and then a corner of each of these red atoms. And then we can make this box another one here, another one here, another one here, right? So by having just this box or just the unit cell, we can recreate the whole crystal. So the crystal and then the unit cell. And now that the question had a third response, which was a lattice, right? And so a lattice is a repeating building block, is a repeating pattern, just like a crystal, except it might not have all the information you need to really recreate the crystal. So for example, we can talk about the blue lattice, the blue atoms lattice. So that would be the pattern that the blue atoms exhibit versus the red atoms lattice, which is the pattern that the red atoms exhibit, right? And so those are two patterns, but they aren't a crystal, right? Because they're not describing the full element, all the element states. And they're not a unit cell because it's not the smallest building block. So the lattice is another pattern that some atoms might exhibit, but not all atoms. And so in material science, we often talk about the anion sublattice and the cation sublattice, or the oxygen sublattice, or the lithium sublattice, or whatever element in particular you're looking at. It might be important to know about that specific atom's pattern within your crystal. So that's kind of a nomenclature thing. Like, nomenclature is always kind of annoying, but it's important. Okay, and the last question says, during a stress strain test, an engineering stress strain curve will indicate dislocations will be indicated by a dislocation. And the tensor tests. What? During a stress strain test, an engineering stress strain curve will indicate dislocations will be created by a tensile stress, the maximum, B, the yield stress, or C, just before fracture. Yeah, so the answer is B, because the yield stress denotes the end of the elastic regime. So stress, strain, elastic. Okay, so we have stress and strain on the y, x and y. We have the elastic deformation, which is reversible. And then we have plastic deformation here. During plastic deformation, there is dislocation motion. And this point here is called the yield point, and that's the inflection point between reversible and irreversible deformation. Reversible being elastic, and irreversible being plastic. So in that case, the answer is B. Okay, cool. So with that being said, that's disgusting. Okay. Okay, so critical resolve shear stress. So critical resolve shear stress is an important concept in material science because it is basically the amount of stress required to induce significant plastic deformation. So if we have a crystal, right, this is our crystal, and we apply a shear stress to it. So we'll, on one end, we're pushing this way, and the other end, we're pushing that way. So I go like this. We will cause the atoms to move, and atom motion and dislocation motion is what we attribute to plastic deformation. Now, if this is a single crystal, right, or if we want to have an atom to move, an atom can move in any direction, right? Like you can move, you can apply stress and push an atom in any direction, but there may be a direction that is easier to move in than another direction. And so this idea of that atoms are stronger or weaker in one direction comes into play here because the direction on which it's easiest to move is the most likely way the atom will move, right? So if this is our array of atoms, right? And say, let's get rid of this one. So say this is a vacancy, right? And this is the atom we want to move, right? So the atom, when we apply a stress to it, the atom's most likely going to move to the vacancy because that's one bond length away. That's easy, right? If we wanted the atom to move to this position, we could apply a stress to that, but that stress is going to be larger to get the atom to move to this position than to get the atom to move to this position. That's the general idea. And so it turns out that there's some patterns that occur, and in different crystal systems, there's different planes and directions along which atoms are most likely to move. So okay. So here is our unit cell, and now I'm going to draw. If this is an FCC system, if this is an FCC system, the plane on which they have the most atoms will be the easiest to move along because those are the most positions on the plane. In that case, that is the 1, 1, 1 plane. So I drew the 1, 1, 1 plane here. And what we can see is that we have an atom in the corner, in the middle, in the corner, in the middle. Right, so there's 1, 2, 3, 4, 5, 6 atoms on this plane in this unit cell. So those 6 positions that an atom can reside on this plane. And that's the densest plane in the FCC system. So it will be easiest to move along this plane because those are the most positions to move to. And now moreover, if you have an atom here, this atom will move up like this or over like this, right? And if we remember our crystallography, that is in the 1, 1, 0 direction. Right, so in the FCC system, the plane with the most amount of atoms on it is the 1, 1, 1 plane. So we call that the close packed plane because it has the most atoms in it, meaning when we try to move atoms around, atoms are most likely to move along this plane because there's the most spots for it to jump to. And if you're moving along this plane, if you're moving along this plane, you're most likely going to move in the 1, 1, 0 direction because if you're here, you're going to move along this line to the next spot or up this way to the next spot, right? So you're moving along the 1, 1, 0 or the 1, 1, 0 family of directions. So this is for FCC. We move along the 1, 1, 1 plane in the 1, 1, 0 direction. The other unit cell we talked about a lot was BCC, body centered cubic. Now, body centered cubic, there's actually some cool geometry about this, but the body centered cubic and face centered cubic are the reciprocals of each other, the inverses of each other. So on the body centered cubic system, you will move along the 1, 1, 0 plane in the 1, 1, 1 direction. And I guess, so these denote, let me erase this. So I just use parentheses here for my planes. That's denoting one plane. If I want to talk about the 1, 1, 0 family of planes, I would go like this with the curly brackets. Likewise for my directions, I just use these like square brackets. This denotes one direction. If I wanted to talk generally about all of the 1, 1, 1 directions in a unit cell, I would use these alligator brackets. Okay, cool. So now we've discussed how atoms are most likely to move where they have the most spots. So they're most likely to move on the close packed plane. And they're most likely to move along that plane in the close packed direction, which is, and so in FCC unit cell, face centered cubic, they're most likely going to move along a 1, 1, 1 plane in a 1, 1, 0 direction. In a body centered cubic material, you're most likely going to move along the 1, 1, 0 plane in the 1, 1, 1 direction. Parentheses denote one plane, squarey brackets denote a family of planes. These guys denote one direction, while the alligator brackets denote a family of directions. So to get back to critical resolved shear stress, right? It's the idea of that if we have a crystal, right? A crystal is aligned in space, and we have all of the 1-1-1 planes that the atoms are most likely going to want to move along. So okay. Okay, so yeah, so this is our specimen. It's a single crystal. It's a single crystal, and we want to pull on it to break it, to induce plastic deformation, but we don't know along which direction to pull, essentially. So what we're going to have is right? So we're going to pull on it with some stress, and we're going to call that the applied stress to the system. But sometimes when we pull on the stress, it might take 100 megapascals to break. And sometimes when we apply a similar sample, it might take 200, right? There's a lot of inconsistencies to this. And the reason there's inconsistencies to this is because we're pulling, the crystal might be oriented in different directions, but we don't know that because we just see the sample. So when we see the sample, we pull on it, like, okay, it breaks. And we do this 100 times, and we're getting a large range of values. And that's because each crystal has a slightly different orientation of the 1-1-1 plane, right? So if this is our 1-1-1 plane, right? And when we apply a stress to it, we're taking an atom and we're moving the atom in the 1-1-0 direction, right? That's what we are trying to do. That's how we're trying to break the sample. And yet we're applying the stress in this direction, right? So depending on like, you know, this angle between not only the plane, we have this angle here, we also have this angle between the direction. We're going to be getting different stresses required to break the sample, just because like the orientation is different, right? So if we're pulling along the 1-1-1 plane versus pulling along the 1-1-0 direction, it's going to take different amounts of stress to really cause crystals to break. And so that is modeled the critical resolved shear stress is equal to the applied stress times the cosine of the angle between the applied stress and the plane and the cosine of the angle between the applied stress and the direction. Because you can't be too close to the plane or the angle, right? Direction, right? If the angle is too small in one, it's going to become really large in the other. Because you're multiplying two cosines together. And so the way you maximize this, like, so the way we would get the highest value of this. So wait, so now the question is, okay, this is our relationship. And we want to break the material, right? We want to induce plastic deformation, but we want it to take as little energy as possible. So we want to maximize or minimize this applied stress that we have to apply, right? So how do we do that? Is we minimize this value, right? Or so sorry, rather we maximize this value, because if we make the denominator really big, then this number becomes smaller, right? So the way we maximize the sum of two cosines is if we, like, you know, we could do this out. Like, we can say, oh, the maximum value of these cosines is this, and the maximum value of this cosine is that, right? So, but because these cosines are related through this vector, this value will be highest when they're both 45 degrees. So if they're both 45, cosine of phi times cosine of lambda is equal to √2/2 times √2/2, which is equal to 2/4, which is equal to 1/2. So then what that says is that our critical resolved shear stress is equal to or more So now at this point, at this orientation, we find the relationship where the applied stress and the critical resolved shear stress is the smallest, right? It's just a 2-to-1 relationship. And then because we know that the critical resolved shear stress is a constant, we know this is a constant, right? We can, when we test an unknown sample, we know our applied stress and we know our critical resolved shear stress. So depending on how much stress requires to break the sample, we can back calculate our angles. We back calculate these values, and that allows us to know the orientation of a crystal. Because crystals are also anisotropic, right? So the whole reason we do this experiment is if we grow a crystal very specifically in a very certain direction, we can break that crystal to calculate the critical resolved shear stress. That gives us a constant for each material. It's a constant value. Now, when we have a sample of unknown orientation, we can break it. And through this relationship, we will know the critical resolved shear stress, the constant, and we will know the applied stress. That will give us the ability to calculate these two angles, and that will let us know the orientation of a crystal. So now when we build our device, we make sure we put the crystal in the right way to get the right result. So yeah, so this concept, it requires a lot of the building blocks that we've discussed before. And last week I wasn't quite ready to discuss it, kind of just happened. So I'm glad I was able to take this time to correct it. So again, the exam is on Thursday, the 22nd, during lecture time. We'll have recitation again on Wednesday so we could talk some more. But if there isn't a lot of questions about the exam, we may move back to phase diagrams. So good luck, and I'll talk to you soon.